hear me? This is Yehu.
Yeah.
Yeah. What affects the recovery is the rate at
what contributes
which
the numbers
the
here?
infected
Mm-hmm.
the infected people that have recovered by alpha.
Okay, those infected that have just recovered minus what is leaving
Minus
that
those,
compartment?
minus those that are getting susceptible again.
Exactly.
Yes. Yeah.
So minus the susceptible. Those who are getting susceptible, that's 1 over D.
Over B.
So that's how we develop the equations. But then we also have the equations for the mosquito. So it's the same thing for the mosquito. It's so ds instead of h, dsm over dst will be affected by, so the mosquitoes that live at the rate beta. Remember, the rate of living is so beta times. It's now the susceptible mosquito and the infected humans. So if you look at here, it was the susceptible humans and the infected mosquito. But remember, here it's the mosquito which are susceptible. So it will be S of M, I of H. They are biting infected humans. And then beta, the infection rate, force of infection for the mosquito. Then that would be plus the infected mosquito. But then we said in our example, let me just go to the example again. We said mosquitoes in the infected compartment do not transit further in this basic model. What does that mean? Di mosquito dt is equal to 0 because we don't have any change in the mosquitoes. Is that clear?
That's right.
So see, we have 28 minutes to the top of the hour. I think we can use the remaining 28 minutes to see how we can do this then in R. But then the gist for this session was actually to show us the thinking behind developing these equations. Just be mindful of where you're coming from and where you're headed to, what is contributing to that specific compartment. Whatever is leaving is minus, whatever is entering is plus. And one thing that you'll appreciate is that those who are leaving here will be plus here. Those who are leaving here will be plus here. Those who are living here will be plus here, because now they are living here going to the subsequent compartments. So that is the idea behind it all. Any question as I transit back to the Did we have any question? Sorry, I missed that. If there were any.
I was inquiring, Ibrahim.
Yeah, yes, Ibrahim.
Yes, how the IM is equal to 0. I'm seeing an arrow from SM, then another one going to susceptible. Just clarification.
You're seeing an arrow from, let me repeat that again. Come again.
I'm seeing an arrow from SM coming to IM. Then another one from IM going to the susceptible.
Oh, yeah. So there's a point that you missed. Remember?
Yes.
This infected mosquito have to interact with human being is susceptible, right?
Yes.
For the human to be infected, because the mosquito is already infected and the human being is not infected. So they have to go and bite them.
Okay.
That specific arrow is dashed. It just shows the interaction for malaria to occur in the human population, but it doesn't in any way affect the population of infected mosquitoes. It just shows the interaction. So you don't include it in the equation. Is that clear?
Yes, thank you very much.
Okay, now let's go to R. I'll be a bit fast because so I'll just share my screen. And that is it. Let's see first what the publication did. But this publication had a bit of differences to what we did. Where the equations. So I just got this publication online. I'll share it with Abel. So they're saying that here they had background birds, and then we are having, now this is case of H, human susceptible. You're seeing that the human susceptible, they interact with the infected mosquito at that rate of infection for the humans, and they are living, so is minus. Plus, so this is row of recovery. So this is definitely coming from the recovery compartment. So this is the rate of transition, losing of immunity. This was our 1/D. If you think of 1/D as using a notation row, this will be it. And then because we have people dying in that compartment here, the exposed will definitely be now this part here coming there as a plus. And then here we have so we have the deaths mu in the exposed plus this is probably the transition to the infected. And if it's the transition to the infected, because it's a minus of EH, it will now come here, contributing to the infected. And here the gamma is probably recovery, we'll see. And then this, of course, negative times positive is negative. These are background deaths. Now, if they're going into the recovery, this delta, because it's not here, this was probably the recovery. And if it's in the infected, this is possibly the disease-induced death. Let's see. Delta. Yeah, could be the disease-induced death because they're leaving and now the gamma is going there. The disease-induced deaths. And then minus, sorry, that was it. So this recovery, those who've recovered at rate gamma in the infected compartment, the infected who have recovered at that rate will now come to the recovery, minus those who are dying due to background, plus, so we have something else adding to the recovery. So we'll see what that is, minus the row. The row is possibly those who are now living back to the susceptible because it was an SIRS and here they are. So let's see what these guys did here. We have some people coming into the recovery. Oh, we have another person coming into the recovery. So that is what was factored in. We didn't consider that in our model. And then we have the vector. It's basically the same. For the vector is now force of infection for vector. The susceptible vector, which is mosquito in our case, biting an infected human. And they can die. They can die. So when they leave, they come to the exposed. Here they had exposed vector, which we didn't have, minus probably the infected now, they become infected vectors, and the deaths, background deaths. So the infected, when they leave here, because they've already been infected, they don't belong here anymore. They belong to the infected. They now go there. They can also die. So that is the whole gist of developing these equations. It's not hard. And these parameters, they're not standard. You can use anything you want. You can even draw a cap if you want, but that's not mathematical. So we go to R. I will change this to white so that then it is clear. We now see how we can, I hope someone took a screenshot of the equations. let me just clear these things. Okay, so I will open a new. I hope you've all been introduced to R. That is my assumption. So I'll save it somewhere. Okay, so the most important package that I use for these, we'll have to load the package. So we say load the dsolve package. That is what I use. And so loading a package in R is basically library dsolve. And then the next thing you're going to do, let's define.
Excuse me, Robert.
Yeah.
Excuse me, Robert. We can't see your screen. I think we stayed on the screen of the slides. We can't see what you're doing.
I can see the I can see his arrow.
Yeah,
Maybe it's on your side.
Sorry for that. Sorry for that.
Dennis, it should be on your side.
Yeah.
There's visible this side as well.
Okay,
Robert,
let me stop sharing.
No, Robert, I think you're clear. It is only on his side.
Okay. So we'll define the function. And this is how I like to go about it. So I'll first do ES of H. And then I'll do represent DS, the DSH, DT. So I hope you have the formulas with you there. So, and then after there, people are going to the exposed for humans. And then people are going to the infected for humans. And then people are going to the recovery for the people. And then we have the susceptible mosquito. And then we said that we have the infected mosquito. So I'm just putting them as comments first to avoid errors, and then I'll remove the comments. So what defined that? We said that, let me look at my phone. Anyone who has the equation? Okay, we said that it was beta, and they were living, so it is beta of H. Remember, it was beta of H times, because it was susceptible individuals, S of H. So this is the force of infection for humans, susceptible humans, compartment, times the infected mosquitoes. Basically the formula that we used. And we say that this component now here is coming back here as a, adding to that component as a plus. But they can live at the rate alpha. Let me see, they can live at the rate alpha of E, yeah, E of H. They are leaving the EH compartment now. And those who leave the EH compartment, they are coming to the I of humans. They're coming to the I of humans. And then this can live at gamma times. So they are living at the rate of gamma of now the I, because they are leaving the I. Remember, they're leaving the I. These are leaving the E. These are leaving the H. So when they leave here.
Doctor, the first question is missing. Those that are coming in from the R.
The first one we forgot.
Sorry?
The recovered ones.
Missing
The first
people.
question.
Oh, yeah. So I left it out because we want to see cumulative, but I'll include it later. We'll just see how it works out. I just want to be able to see at the end of the simulation period how many people were susceptible in total, or rather had left the susceptible. But we'll just see. You can. That's why you say some of these things we can calculate, and that's what we want to see. Thank you for that. But now we are saying it was 1 divided by the duration, our duration. Just use our examples, it was times, now these are leaving the R. Okay, save, and now we go to the mosquito. So for the mosquito, it's the same thing. So I'll just copy these because they are leaving. But now they are living at the beta of mosquito. That's actually the whole thing. I'm doing this so that then we understand how these things play out. So beta of mosquito, and then it was the susceptible mosquito biting the infected humans. And then this here will go back to the I. But then because the I of mosquito is said for this specific example, they don't change, we use 0. So allow me just to use this so that then we don't get any errors. So that's the first thing I normally do. And this is, to me, the easiest thing when it comes to numerical simulation in R. I just first write the formulas because this is now what I've gotten from my own knowledge and now interpreting the subject matter. And so what's next? We're going to call this, let's call it malaria, or the is. And then it say, because it is a function, we need to get time from there. And the state variables, so we just call them state, and it will be a function of the parameters as well. Parameters. So we have to have some parameters. So I don't know why this was an error and it's a comment. Oh, so that is how it is. But here we need to specify that the state variables and the parameters are as lists. They are lists. So that is the other part. And this one, you can always find these formulas online. And because there are more than one, you just need to specify the state and parameters as lists. So that's how it is. And then there, let me see. So we open that function. We need to open another function. So yeah, with those, and then we open another one. I hope that's the case. Yeah. So, and then I'll just throw in this here, convert them back. Just to explain is that we are creating a function of time that takes time, state variables, and the parameters for transitioning. And time because we want to look at the changes over time, and the state variables because we have SEIR, and the parameters that define the state transition. And all of this will be referring to the parameters of change and the state, the current state and the parameters of transition. So that's what that means. But what do we want to get back in return? What do you want to get back? So here I'll just put a comment that our infected mosquitoes do not transit further. So what do you want to get back? We want to return. What do you want to return? We want to return a list of what? So we want to return a list of all these, the numbers of how all these change over time. So the thing is DSH. We want to return a list of all. I'm using concatenate because it's more than one. So DR, so we have 11 minutes. So SEIR.
I think, Robert, don't mind about time.
Okay.
Let's take our time and we keep learning until our colleague joins us. He's joining from the US. I'm not sure the time zone there. It should be quite early for him, but let's proceed.
Okay, thanks for that. So we will run this and see if it works. Okay. So the next thing we are going to do, we have to set the initial conditions. So we are setting initial conditions. Set initial conditions. So initial conditions means where do we want all of this to start from, or rather to start at. So we are saying for our case here, so we'll set the initial conditions for S of H. So just put them here. All this. So I want to specify the initial conditions for all these. And I will store them. I will store them in an object called initial state. Initial state will take more than one value. So let's come back. Put them there. Okay, so let's say in the beginning we have we have like 99% people who are susceptible at the beginning of the disease. So we say 99% of humans are susceptible at the beginning. And then, so the infected will be, if it's a proportion, definitely will be 99 minus 1. So 1 minus 0.99. So 0.01. 0.01. So we come here and say 1% of humans are initially exposed. Okay. So they are just exposed, they need to transit, so we don't have any infected because they will in transit. So no human is initially infected because then this will come here automatically. It's just a disease progress. Nothing has to happen, just a matter of time. And we are not factoring in background deaths at this particular moment. So they just have to transit. And then the recovery, because no one has been infected, the recovery will be 0. So no human. So we just say no initial recovered human. And then we go to the mosquito. For the mosquito, let's assume 95% of mosquito are susceptible at the beginning. They don't have Plasmodium falciparum. Only 5% of them have. So that would be 0.95. So 95% of mosquitoes are initially susceptible. And then 1 minus 95%, 0.05. 0.05. Because this is the last one, I don't have to put a comma. 5% of mosquitoes are initially infected. Okay, so we store that in an object. Okay. Let's see, initial state, okay. And then what else? Now we need to give these parameters values. Let's say we went to literature or analyze our data. We got the value for beta. We got the value for alpha. We got the value for gamma. We got the duration. We specify it was 2 weeks. What else? And the beta M, yeah. So each of those. So I normally like copying so that then I don't forget any of them. So the parameters, we had beta. The next parameter, that's beta H, alpha. Alpha, sorry. And then after alpha, let's see here, alpha, gamma. So gamma, And then after gamma, let's see. So we have our D, duration, and we have our beta M. So beta for mosquito, and then we have our D. So these I'll just call them parameters, yeah, because you have to call them the same name that you call them here. So just copy, paste, see, that's highlighted, so that means it's the same name. And then convert those up there, and then give them their values. So the beta, let me see, I had some values somewhere that I was looking at during lunchtime. Okay, so the values of beta here, I had 0.2. And these are just say transmission rate. You can get this from literature or calculate from the data. Transmission rate from mosquitoes to humans. And then, oh, sorry, I forgot to assign. So such simple mistakes can cause you. Alpha rate, alpha, the incubation rate, we had 0.1. Then you can see this incubation rate, remember? And then the gamma was the recovery. We had 0.05. Then we call it recovery X. And then the cause of infection for mosquito. Let's call it that. And then our duration was 14 days, so that's 14. And let me see. Okay. So ideally, malaria, let me see. We captured that. So it's saying almost 1 year. So I just got this from literature. So we say that someone loses maybe 1 year. So all these values, the values that are put here, they are not important. They are not standard. This is what you'll get from your literature review. This is what you'll get from your data analysis of what. But now defining them is what is important. And you can appreciate that from the very word go, apart from now setting up this function, which is a standard thing, all the other things are things that you can do even without knowledge of R. You can just do them. And these, you can just copy them online. You can always find these online. You don't have to master them. Okay, now the next time is to define the period time for the simulation. So simulation period, we want to simulate this disease. So remember, this is a naive population, but not really naive because we have 0.1%, but it's almost fully susceptible. So simulation period, we want to simulate this thing for 1 year. Okay, so how did we call that? So we called it time. Okay, so we want to simulate this thing for a period of 1 year. So times, so we say it's a sequence from 0 to 365. 1 day, let's see if this will run fast. Okay, 5, okay. Have times there. So what else? Let me see, what else? Now to solve the ODs, because we have our time, we have our state variables, okay, we have our parameters. Now to solve the system of ordinary differential equations. So here to solve, now we will use the ODE formula. And the ODE, as you can see, here from the moment you write ODE, R will show you. So it wants the Y why we'll have them as our initial states, the S, E, I, R, S of M, and pi of M. And then it wants the times. So the time we will give it, we already have the time. And it wants the function. So we've already created our function. Here it is. Here is the function. What else? Let's see. What else? The method is not important. Okay, let's run it. So there, so Y is the initial state. And then what else? Function. Times, we have it as times. We've created an object called times. So we're just now, we are assigning, and the function, we called it malaria or disease. Yep, that was our function. And then the parameters, call them parameters. Let's see if this will run. So that's it. There's nothing else we are supposed to do. And this you can also get online. So let's save it under it. See if we get something. So it's saying S of H not found. So sometimes saying S of H not found. So what I'll do, I'll try and run them individually. Okay. Run them individually. Oh, sorry. Sorry for that. It's actually meant to be this way because it's not changed. We are assigning the actual state, the number at that particular time t. So it's not the change. Sorry for that. Okay. So we have our results. Let's see how our results look like. So result, like converting it to data table. So I need to load the data table so that I can access this function. And let's see what you're having. So we are seeing that from time 0 to 365 days, this is how the numbers are changing over time. And because we assumed proportion is all the way from 99% to, at the end of the time, only 1 to 2.5, 2.3% will be susceptible. And at the beginning, only 1% was exposed. At the end, 5.7% will be exposed. There was no infected at the beginning, as we said. At the end, a total of 14.2 at the end of the time, but then we can get the maximum. And then they recovered. We can see people recovered, and then those who are recovered start going low, down. And then we have the susceptible mosquito at the beginning. That was 95%. At the end, only, that's so less. That. And then the infected mosquito was always constant, because that's how we specified here. There's no change over time. So if you have a Cartesian plane, if you have these, let me draw it this way, how we used to. And we've said that we've said that it's 0 over time. So if the M, the IDM, and these are the number of mosquito, and we are saying that the change in mosquito over time. So just imagine this is the T. So, and this is time, and these are the number of mosquito. If it's 0, it will be constant over time. That is why we're having all the zeros through. So
yeah,
okay.
Robert, this is very helpful.
Yeah. So I just wanted to plot, if time allows, we see how they look like on a plot.
Yeah, I think let's plot.
Okay. So I'll do this and close this. So I like plotting using ggplot. So I'll just load the library ggplot2. And so I'll just follow this. I'll plot the humans only for this example, but it's just the same. If you want to plot results, for me to be able to access that piping operator, let me load ID first. So we are saying that we want to gather from here to here, but gather is outdated, so we'll use pivot long, and we only want to deal with the humans, so we'll do away with these two for now. So we'll say select. We want to select minus S of M and I of M. See if that has worked. Okay. So did I load the tidyverse?
Yeah, you loaded it.
Okay. Let me just repeat. Okay. Let's specify and see. Okay. So we want now to gather that so that then we can be able to draw them in one plot. So we want to gather from X of H to R H, and then the names will go to, let's call them the compartment. And then the values will go to, let's call them numbers. But you can always find a better name. Okay, now we have them. Time compartment numbers. And then we want to do ggplot. Static. We want our x-axis to be actually time, y-axis to be numbers. Then we want the color to go to compartment. Let's see if that will work. Sure. Okay. Now we want a geom line. Sure. Okay. And I'll just push this there. We can add a title. Let's say area. Okay. Position the title. Midway. So I hope you can all see. We can sorry for that. We can all see this one, and we can describe now. We can describe now this. You can see these are the number of recovered over time. Yeah. Someone to please describe. Go ahead.
Yeah, no, I'm just suggesting that we will continue with this. This is very exciting. Our next session is in. Our next presenter is in.
Oh, sorry for that.
No problem.